The following presentation was recorded at the 2025 Southeast Linuxfest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information on the Southeast Linuxfest, visit www.southeastlinuxfest.org. Come join us next June.
Okay, everybody. Wonderful to be here today. My name is Bruce Momjian. I live in Philadelphia. I work for Enterprise DB, but I am also more well known as one of the Postgres core team members. I've been working with Postgres for 29 years now, and I love my job. I have a lot of flexibility, and one of the exciting things about that is being able to do research, being able to travel. I travel about 80 days a year. I attend about 30 conferences a year. This talk actually was birthed at this conference last year. I'm not sure how many of you were at the talk. I believe it was about semantic search. And it was not in this room, it was in the room along the wall with the glass windows. Was anybody in that talk? Does anybody remember that? Well, okay, great. Were you the speaker or no? You weren't the speaker, though. No. So when I went to that talk, I was really interested to see how to use semantic search. And one of the things that came up was that there was these embeddings that were fundamental to semantic search. And I asked the speaker at the end, and again, I recommend that as part of this conference, any conference, if you have a question, find the speaker, ask the question, because that's why you're here, is to be able to interact with the speaker. And I asked that speaker, where do these embeddings come from? Right, and I'm going to explain exactly that in this talk. And the speaker said, I don't really know. I'm not sure anyone does know. I'm thinking, well, it's something to that effect. Maybe I'm not being accurate, but I've heard that type of expression before when I've asked other people about this. And I'm like, well, these embeddings don't come out of the sky. They must come from somewhere. Someone must know where they come from. And having left this conference, and my employer, EDB, has been getting much more serious about integrating AI in databases. I said, I need to figure out how these things work. And I decided that that's what I was going to do. So I spent about, a while, maybe 6 weeks, researching exactly how this whole AI thing works and how does it sort of integrate with Postgres and so forth. Excuse me a second. Poor form to be wearing your lanyard, I've been told by my wife, for a speaker, so I had to take it off. So the question is, how does AI work? Where do these embeddings come from? And honestly, it sort of started as a question of trying to understand something. But effectively, what I realized was that I couldn't explain to people how to use databases for AI unless I actually understood how AI works, right? You can't look at a technology and figure out, okay, how is database going to help it unless you understand the foundations of how it works. And what this slide deck is actually for, and I've delivered this slide deck in 25 minutes and 65 minutes. So I know that sounds kind of like a wide margin, but effectively those are the time slots I've given you. Today we're going to do it in 45 minutes. So let's get started. My name is Bruce Momjian. This is my website right here. There are 63 presentations there, about 2,800 slides, a QR code. Most of them are about Postgres. There's a small number about open source. So I've given those talks here. I've given home automation talks here. Tomorrow I'm going to give an hour, 45-minute talk about cryptography and the mathematical or the foundations of cryptography. So if you've ever, again, same type of talk, if you ever wanted to understand exactly how things work from the bottom up, that's sort of my specialty, I would say. That's what we're going to do today. That's what I'm also going to do for cryptography tomorrow. So this is actually a second AI talk for me. I have Postgres and the artificial intelligence landscape. That's actually a really good talk. But again, that was written before generative AI became popular. And in fact, there are videos of me giving that talk if you wish to look at it on my website. You can also look at videos. I think there's 130 videos of me giving various talks. So again, you can go to my website and see a lot of that information. Now, the talk I wrote about the landscape it talks about artificial intelligence, talks about machine learning and deep learning. It has a demo using Postgres and PL Perl. And finally, again, finishes with how does a database really help here? And that's how I'm going to finish this talk as well. But today we're going to talk about a very broad topic. And again, I hope that it's helpful. I would have loved somebody to give me this talk a year ago before I had to do all this work. Because unless I've been a type of person that unless I understand the fundamentals of something, I can't really use it. I can't really harness all of the capabilities. And as a career person, and I give career advice occasionally, one of the things I've advised people is to find technology that's foundational, whether it's AI or relational or computer hardware or Unix, Linux. And once you find a foundational technology, understand that all the way down. And once you understand that, you'll be able to use that knowledge for me, certainly for decades. Very rarely do you spend there's a lot of people who study technology deeply, but if they don't choose foundational technology, I'm thinking of Microsoft technology particularly, it comes and goes. What was good today is different tomorrow. I try and identify technology that is foundational and study it deeply, and therefore I have that sort of in my tool belt. Not a whole lot of 63-year-old developers still kicking around at the top of the field, but that's where we are. So we're going to talk about the AI explosion. I think everyone is super excited about that, and I'm going to try and give the realistic view of why it's big or not. We're going to talk about something called hyperdimensional arrays. I apologize if some of you are allergic to mathematics. I will try and be gentle, but we have to cover that to understand it. Then we're going to talk about how training works. This is the effective thing that I decided I was going to study when I left the talk about semantic search last year at this conference. How does that training work? Then we're going to get more specific. We'll talk about semantic and vector search, particularly with Postgres. We will talk about something called transformers, which is foundational to generative AI. Then we'll show you how generative AI works. We'll talk about retrieval-augmented generation, or something called RAG, if you've heard of that. And finally, we'll finish up talking about deployment options, particularly where is a database good here, where can it help, and then finally a conclusion. So AI explosion, I know a lot of you are still adjusting to this. I was actually at a Amish Mennonite church about 2-3 months ago, and they have a tradition of inviting visitors to their house afterward. But I've attended that church for a while as a visitor, so I kind of said, maybe you just go home. Don't worry about feeding me or anything. And they said, no, we'd really like you to come over. We have questions about artificial intelligence. I'm like, okay, that is something I know a lot about, and we indeed did talk about it. So if you're wondering whether this is a topic that is relevant to people, it certainly is. And I think one of the things that I hopefully we'll do at the end is to set realistic expectations of what it can and can't do. But not from a listen to me, just trust me kind of thing. I'm going to explain exactly why the conclusions that I come to at the end are foundational. But really the start of this whole buzz about AI started November 30, 2022, not a date that would really resonate with anybody, but in fact, the first day the ChatGPT-4 became available. And the ability to do human-like conversation, the ability to generate images with DALL-E as well, really shocked people. If you're looking for more information, the URL here in the middle is actually a 6-hour YouTube series about generative AI. It is very complicated, very mathematical, but it is the best AI series that I've seen. The URL there at the bottom is a quote or an article about how ChatGPT changed AI so foundationally. Again, if you download these slides and you click on the blue, it'll take you right to those to those sources. You'll see these blue links all through this talk. So again, if you want more information about a specific slide, that blue is where you go. I mentioned that I had a talk about AI before, and the talk I had about AI before was what we knew modern AI to be, and that we now understand to be what's called discriminative or predictive AI. And in discriminative predictive AI, we basically are worried about classifying things, fraudulent credit card charges, for example, image recognition. We want to do recommendations. We have predictions of trends and even language translation. So this is pre-2022, what people basically, the public basically considered AI to be. And with the advent of OpenAI, with ChatGPT and then DALL-E 4 for images, we have the ability to generate content. That is the transformative issue of generative AI. Think about it. It's called generative AI because it's literally generating something. So it's not a bizarre title. It actually I think is very descriptive. Now, generative AI use cases, I think we're still trying to figure out what these are, but we all know things like chatbots, which are usually incredibly disappointing to me. Semantic and vector search, which I'm going to show, I think is tremendously powerful and a powerful tool for application developers. The idea of summarizing text is actually a separate AI skill. I know it surprised me, but summarization is basically a specialized AI generative tool. Language translation, I think we've made big strides by using generative AI there. Of course, image and creation of images and searches. And in the software area, the idea of code generation, code analysis, data analysis, even programming language conversion, I think is powerful. So to kind of split it apart, we have discriminative, which is mostly what we call supervised learning with known outcomes, very domain specific. And again, the output is the determination. Generative is generating new data. It requires massive amounts of data, but is more general and obviously outputs new content. So just to give you a visual for this, this is what discriminative is looking like. Discriminative is trying to identify, using AI, the boundaries between categories. Things like dog, cat, or valid credit card charge, invalid credit card charge. It's trying to generate those boundaries using data sets. In generative AI, we are effectively using vectors, and I'm going to explain that in the next section. But again, foundationally, it's a completely different thing that we're doing here. So I promised, or at least threatened, that I was going to talk about mathematics, and here we go. Mathematics, having been a math minor and a mathematics teacher for 5 years in high school, 4 high schools, I kind of like it, but again, we'll do the minimum. Numbers, obviously, in mathematics, you can represent numbers that aren't really representable in the real world. So, for example, how many atoms in the universe? 10 to the 80. Does that mean anything to me? No, it doesn't. I don't know what that is. Infinity, obviously, that's a really weird concept. And even things like calculus, and where you're doing infinitesimally small adjustments or summing infinite sums. Again, this is not something you can do practically. You can't infinitely do anything in the real world. But again, in mathematics, we can represent that. And we can represent it physically, we can represent it as computers or even an abstract. So again, this concept of duality is sort of an issue for what we're trying to do here. But most AI, generative AI, is using vectors in a 1,000 or 12,000 dimensional space. Now, we live in a 3-dimensional space, okay, length, width, height. 4 dimensions is kind of a stretch. If you add time in there, it's really not the same as the other dimensions. It behaves differently, but it could be called a dimension. But when you're talking 1,000 or 12,000 dimensions, that's just way out there, frankly. This slide is trying to show you 10 dimensions because in the top right, you can see I have a point pink, and then in that I have an XY at the point, and that has another point, and then at that point there's another one, and I do it 4 times, then I get 10 dimensions. So imagine going to 1,000 or 10,000. Space is massive, certainly much more massive than we've ever dealt with in the physical world that you or I are familiar with, but it is a foundational requirement for generative AI. And we typically use 4-byte floating point numbers in here. You can use 2-byte as well. But effectively, again, each axis of this 1,000 or 12,000 dimensional vector has a floating point number representing where it exists on its own axis. Is that at least palatable for everybody, I hope? Again, the vectors are kind of, you basically have the vectors of different directions. They all have the same distance from the center. Typically in a generative AI case, again, some URLs here at the bottom for detail. So that's enough of the mathematics. Let's actually talk about what I came here to talk about. And the question that I had a year ago, how do these vectors, this embedding thing, how do they get trained? How do we assign vectors to words or numbers or whatever it's doing? How does it happen? And we're going to walk through this, again, 4 URLs here at the bottom to sort of help you walk through what the meaning of these things are. So let's just walk through a typical training case. So we basically, let's suppose there are 30 or 50,000 words in the English language. Now, there are other ways of doing this. You can use fragments of words. You can use what we call byte pairs. But again, I'm just going to make it real simple. Let's assume we have 30 to 50,000 words. We're going to create a vector for every word in the English language. Just doing English, okay? And we're going to assign them a random direction in this 1,000 or 12,000 vector space. Just random. Now, these vectors are nowhere near each other, right? You're in 1,000, 10,000 dimensional space. They're just like floating in a space with nothing near them. 30 or 50,000 vectors in a 1,000 dimensional space is just, there's a lot of space of nothing. Okay, so you just randomly throw them out there. I don't know why, but you just randomly put them there. And then here's where the training happens. What we do is, as we go through documents, we look at words and words adjacent to other words, and we adjust the vectors to be close to words and other words that appear in the same text. And we potentially do that for every web document that exists on the internet. And once you're done that, you effectively have a trained text embedding for all of these vectors. And I know that sounds improbable, but let's walk through that and I'll show you exactly what it looks like. Okay. So let's take an example. Like I'm just doing king, queen, man, and woman. This is a classic. The bottom here is a Stack Overflow URL. This is the classic example of how you basically take 4 words and just randomly put them in a 2-dimensional space. Right? Very simple. Okay. And what we do is we start to take a text like the king is a tall man, just a crazy example. Okay. And we basically either move the red word nearer to the blue words or the blue words near to the red word. There's actually, at the bottom, he explains the difference between the 2 ways of doing it. There are some advantages doing it one way. There's some advantages doing the other way. I'm not going to get into it. But the point is that I'm moving king near tall and man as I'm kind of walking through this. Okay. So king is getting closer to man. Tall is getting closer to man and king. Here's a bigger sentence. The king is a tall man. The queen is a beautiful woman. They sit together in the throne room of the castle. That's my 3-sentence document that I'm going to train on. So king gets closer to man. Tall gets closer to man and king. Queen gets closer to woman. Beautiful gets closer to woman and queen. Throne gets closer to castle. And then again, king, man, queen, and woman get closer to throne and castle because I'm spanning sentences there. Okay. So again, they're moving. They're not moving in a 2-dimensional space. They're moving in a 1,000-dimensional space. Okay, and what the fundamental difference there is that when you think of moving something closer to something else, you think of it moving, it gets closer to one thing, gets farther away from something else, right? That's usually, if I get closer to you, I'm getting farther away from the wall, right? Just in a three-dimensional space or two-dimensional space. But in a 1,000-dimensional space, I can move some dimensions closer to another word without affecting other dimensions. So you start to get this nuance where a word can be close to several different words, or you can move it closer in some dimension, but not closer in another dimension. All right? And that is really where the genius of semantic search, the genius of generative AI comes in, because you're starting to give multifaceted meanings or closenesses to specific words. Okay, so let's look at this example right here. I have man and woman, king and queen. And when I do all this training, what my output effectively is that man and woman are close to each other because they appear very often together. But also king and queen are close to each other because they appear together. But what's really interesting is when you look at the difference, the distance between man and woman, if you go to king and you add the distance from man to woman to king, you get queen. Because what has happened in all this training is that I've moved in some dimension king and queen close, and in some dimension man and woman close. But the way that the training has gone, in the 1,000 dimensions, that angle is actually the same between man and woman and king and queen. I can actually do things like king minus man plus woman equals queen. This is a very traditional as in 2, 3, 5 years, 7 years ago, foundational sort of example for generative AI, where you're bringing in these nuances, and the nuances actually are transitive to other objects or other words in the text. I know it sounds really out there, but when you do this enough times with enough mathematics in enough dimensions, you start to get this kind of outcome. Now, this is just an image of what it potentially tested could look like. It's not one. It's just sort of, but again, the number, the quantity of numbers for a single word and the number of dimensions that can be adjusted is really, really astounding. Okay, I'm going to stop right here. I'm going to ask for questions. Who has a question? Yes, sir. Oh, sorry. Yeah, back right there. Yes.
I know that recently they started introducing agents into newer technologies. I was wondering where agentic RAG systems, where the agents would come to play.
Okay, that's a great question. Unfortunately, I'm not planning to cover that in this talk, so I'm sorry about that.
No, you're fine.
Other questions? Yep, right there.
I've heard neural networks explained with a two-dimensional graph of a simplistic neuron, dendrite, axon. I forget the biological terms, but are we talking about the mathematical representation of that same idea of nodes with edges that have relative weights when we talk about the hyperdimensional vector database?
So that's a great question. Toward the end of the talk, I'm going to talk about the research that Google did. And effectively what happened there is they'd done a bunch of work on neural networks, and they basically hit limitations that they could not overcome. And what came out of that was this concept of multidimensional vectors and what became known as word-to-vec. I'll have an example later on. So basically, Google had been doing a lot of research. They got pretty far with neural networks, but they pretty much hit a limit because they couldn't. It required too much fiddling by humans to get it to work. And this basically kind of ripped off that requirement, removed that requirement, and basically pushed it into that 1,000-dimensional space. There is a relationship, but I would say this is not neural networks. This is basically a more practical imitation of that goal. And neural networks are foundational to getting here, but I would say this is not that. Yeah. All right, let's keep going. We'll have more time at the end. So now that I've explained the training thing, let's talk about semantic and vector search. Now, Postgres and a lot of other tools have had what we call text search or phrase search, if you've heard that term, for many years. And phrase search effectively is looking at letter combinations, so words or stemmed words, which is what we call it. The word king, the word queen, the word man, the word woman. But we're looking at it really as a set of characters, okay? And what you can now sort of start to think about is that we don't have any meaning behind those characters, right? A man and a woman, a king and a queen, they're just 4 letters, 5 letters, 3 letters, whatever. Okay, there's no relationship between those words. Text, full text, and phrase search just as looking at words. Now you can do synonyms and stuff like that, but it's really very limited. What's really interesting is how semantic search effectively brings in that training data, that understanding of relationships, and allows you to do a much more powerful search than you would with traditional full text search. So let's look at how that works. Typically, you'll download a pre-trained text embedding. How is the text embedding trained? We talked about that. Could be Llama, could be ChatGPT, could be pretty much, there's a ton of them out there. And I'll talk a little bit later about what some of the places you can find them. But you download a pre-trained text embedding, or you create your own training if you want, okay? Then you chunk your document into sentences or paragraphs, and then you find the text embedding vectors for all the words in your chunk. You average those vectors and you store them in a database. So remember, we're going to be searching for some things, maybe a document. So we take a document, break it down to pieces. We take the chunk that we've chosen. We get all the text embeddings for all of those words. Remember, we're in a 1,000-dimensional space here. And we average the vectors of all those words. And once we've averaged them, we just store that average in the database. Okay. And then to do a search, all we have to do is we take the query, whatever that is, we get the text embedding for all the words in the query, we average those vectors, and then we find the closest vector in 1,000 dimensions to the query that we asked. And I'm going to give you some specific examples and specifically show you how it is superior to a normal full text search in a lot of cases. Okay, so how would we set it up? Here's my document. My document is the king is a tall man, queen is a beautiful woman. They sit together in the throne room of the castle. We saw this already. Okay, so I'm going to break it up into sentences. First sentence is king is tall man. Second one's about the queen. Third one's about the throne room. Okay, I've got 6 vectors for the first 2. I got 10 vectors for the second one. Okay, so what I'm going to do is I'm going to average those 6 words. I'm going to store them in the database. Okay, then if I do a search, who is the king? Well, the king, who is the probably or vectors? Who knows where they are? But the king lines directly up with one of the vectors in one of the search, one of the chunks, and therefore the return is the king is a tall man. Okay, now let's walk through some examples. I'm going to use PG Vector. Again, I have a URL here at the bottom for running PG Vector. We're going to install it. We're going to create a document table, which is going to store 3 sentences. And then we're going to create a document embedding table, and that's going to store vectors. All right. So we're going to basically insert into my document table my 3 sentences in Postgres. We're going to create an index on that. And then I'm going to create a Python script, which is going to go out into OpenAI. It's going to send my sentence. It's going to average it, bring it back, and I'm going to store what OpenAI returns to me in my database. So I'm using the training vectors that I'm getting from OpenAI. And here's what we're doing in red. You can see me actually creating the embedding, and then the bottom right, I'm actually inserting that embedding into my document table. So I'm looping through my document table. I'm getting the average vectors for each of the chunks, and then I'm going to store that in document underscore embedding. Is that good for everybody? Great. Okay. So we got our embedding stored here. You can see King's a tall man. We have one vector, Queen is a beautiful woman, another vector, sit in the castle, another vector, okay? How are we going to do our query? We're effectively going to take our query, we're going to send it to OpenAI, it's going to average the text embeddings for us, and then we're going to say, give me the closest, this is the what we call the spaceship operator right here, give me the closest match for this particular key, this particular query. So who is the king? That's an easy one. King is a tall man is clearly the closest. Who is tall? That also gets us king's a tall man, not surprising. Who is short? Well, turns out the king's a tall man is the closest because tall and short are related to each other in semantic search, right? This is a good one. Who is pretty? The queen is a beautiful woman clearly wins there because it knows that, remember, with the training, it knows that pretty and beautiful are related to each other, okay? Who is in the palace? What is the winner there? The castle sentence. Because it knows palace and castle are related. And then where is the chair? That one wins because sit and chair go together. And also chair and throne go together. Okay, so you get a double win there in terms of semantic matching. Any questions? Okay, yes, I'll take the one. Thank you.
So when you're showing this, the thing that's sort of popping in my mind is you're going out to OpenAI to get particular weights to do this stuff, but how is this different from, for instance, like, because you're using semantic in the sense like latent semantic indexing or something like that, where you have query terms where you're mapping it to it, because you have the same sort of word to vector relationship. Like, what's the difference between this and the weights that you're getting here?
And what's the difference between this and full text search? Is that what you're asking?
Latent semantic indexing that does like I think that was what people used before, like going out and calling to OpenAI.
Yeah, you could do that too. I mean, I'm trying to do it where I'm storing the vectors locally, but if I did it, I guess the other way I could do it too.
But this goes out and gets it from
OpenAI.
OpenAI, the weights?
Yes. Yeah. It does it actually right. Here's my AI key here at the bottom. And then it's actually, so my search term is supplied on the command line, and then I send my key, and I'm using this text embedding model right here. And then I'm effectively inputting the search term, which is what I used, and I'm sending it to OpenAI, and I'm getting an embedding back, and that's what I'm storing into the database.
And when you send out the query terms, it's similarly, you're going out to fetch it?
Yeah.
Is there a way that you could just grab all the weights that you needed and not have to go out to OpenAI?
This is a great issue. So OpenAI does not have an API to allow you to download all of the vectors. Now, if you do use Llama from Meta, that will allow you to keep all the vectors local. But OpenAI effectively their vectors are their own, so they don't allow you to download them.
Okay. At some point, you get probably penalized for, like, what if this service goes down and you want to do?
Big problem.
Yeah.
Yeah. Okay. I'm gonna have to stop there. Sorry. So let's keep going now. For generative, how do we generate? Right. We just took semantic search. How do we actually generate output? Okay. This is what OpenAI does when you go to the prompt or get Gemini or any of these systems. So the way that works is those use the text embeddings in a different way. So effectively what a transformer does is it uses something called attention blocks, and it basically walks through adjusting vectors. And let me show you an example. Again, a lot of detail here. There's different type of attention blocks. There's self-attention blocks. There's other types, but we're gonna make it pretty simple. These are some of the statistics that OpenAI uses for its attention blocks. But effectively, what happens is that we take a sentence like, "What is the capital of France?" Okay, and we look up the text embeddings for those. What is that? 6 words, 7 tokens, and we store them in something called an attention block. That's what we're doing here on the right-hand side here, okay? And then what we do is we adjust the first word to be close to the text embedding of the second word, okay? And then we do the same thing with the first 2 words, and we adjust them closer to the third word, and then we take the first 3 words, adjust it closer to the fourth word, and similar all the way out, okay? So all these have been adjusted closer to each other, okay? And then we run this perhaps 96 times, all right? So effectively what's happening is that the new vector, this is no longer this is no longer France, this is adjusted, and we just keep adjusting them. We keep adjusting them. This attention block thing was revolutionary in terms of generative AI. We couldn't do it without that capability. So we're adjusting what to be closer to what is to be closer to what is the, and again, we're multiplying all of these vectors. And you can see it gets to be very computational intensive. This is where GPUs obviously become very useful. But what's really weird is that once you run through this 96 times, the last vector is actually the first word that you're supposed to return to the user. Now, I've simplified this a lot. I haven't really talked about sentence structure and priming and so forth. But the concept is that as you're taking this sentence with these known vectors, with known trained words, you get this like super vector at the end. And the super vector at the end is effectively the word you should return. And we return that word, and then we run it again to get the second word. And so if you've ever typed into ChatGPT and the text kind of comes out like one word at a time, just because that's the way it's generating it, right? It's not like a 300 baud modem. It's actually generating it one word at a time by running through effectively these attention blocks, okay? And this is, again, a lot of URLs at the bottom, but effectively this is the way the generative AI works, okay? So let's run through a pretty easy example. I'm using ChatGPT. We can see some stuff going on. What is the capital of France? Great, capital of France is Paris, easy. How has that worked? Well, the 2 active words there are capital and France. And over time, what has happened is that capital has moved closer to France. France has moved closer to capital, right? Oh, actually, I take that back. Capital has moved closer to France, and France keeps moving closer to capital, and eventually it ends up in the Paris vector, effectively, okay? I can say differently, the capital of France is, I get the same answer. Where is Paris? That kind of is cool. Comes up with a whole bunch of text here. Now, there is another Paris in Texas. So if I say Columbus is in Ohio, where is Paris? Pretty sure Paris is in France, but it also mentions Paris is in Texas as well, okay? Now, if I say I live in Texas, where is Paris? I now am looking at Paris closer to Texas now instead of closer to France, right? And it's basically pushed the generative part to start talking about Paris, Texas. All right. So that's how the generative part works. I want to talk about something called Retrieval-Augmented Generation. This is where we start to get a little bit more into a database, how a database can be used here. So I know Retrieval-Augmented Generation, or RAG, is this kind of weird term. I don't even think the authors are happy with the name, but effectively, what it allows you to do is to prepend some information to the user query. It's really all it's doing. So what I've done here is I've added in red the text I'm prepending. because I'm prepending text, that prepended text is going to adjust how the query gets executed again, because we talked about how earlier words affect later words and change their meaning. So reply briefly, where is Paris? As you can see, that's much shorter. This is how it actually looks when you send it. There's like a JSON, and it has a special role called system, and that's where the RAG basically gets sent. So if I say Columbus is in Ohio, where's Paris? Now it's kind of, it really hasn't talked about Paris. In this example, it doesn't talk about Texas at all, okay? But if I say I live in Texas, it gives me the same text I have pretty much for Paris, France, but it also says if you meant a different Paris, such as Paris, Texas, it is a city. So it kind of adds that at the end. What basically happens is that the RAG information is given less importance than if I had typed in, I live in Texas, where is Paris, which I showed you earlier, okay? This is really kind of cool as a database person. I dumped out some JSON data about an order of a customer. So I picked a customer, they have 3 orders. And I basically said, okay, here's the orders in red, and I can ask all sorts of questions about this RAG information I prepended to the query. When were the orders made? It knows by looking at that JSON where the orders were made. Where is the earliest invoice? It knows how to do that. What's the total of all invoices? Actually goes through that calculation process. What is the average invoice amount? Again, it shows me its math here and how it figured it out. This is interesting. Today is April 15th, 2024. With 30-day payment expected, which invoice are overdue? It knows that. What's the total of invoices that are not pencils? You can do that. It even can guess when the next expected order date is based on the frequency of orders that I've kind of given it. This is powerful. This is potentially something that could change how we use databases and how we allow non-professionals to process. I think that's a real win, is allow non-professionals to actually get at data that they typically would require somebody with relational SQL skill to do. It can even generate SQL queries on the fly, which I thought was pretty cool. Okay, and here's an example where we actually can take the data from a database, prepend all of the JSON invoices before the customer asks a query, and then we potentially could give them a very reasonable answer. All right, and if you think of how chat bots work, that's pretty much the way they work. They prepend some information about the customer, and then the question is asked, and hopefully the prepended data, like when was your last flight or what flights are coming up, can basically be used to answer these kind of questions. Sometimes unsuccessfully, sometimes successfully. Okay, so let's finish by looking at deployment options. Again, you asked about where to host it. You can use ChatGPT, but that's really cloud only. You can use self-managed hosts like Llama. You can do your own public training. You can have locally trained data sets, whole bunch of things. You can go to Hugging Face, has a huge number of these AI models out there. And obviously, you can use Postgres to do the semantic search and stuff like that. This is, I think, the great slide for relational folks, for database people. Semantic search, really good for databases. Text embedding, vector training, transforming of user queries, and are really not user vector training, not good for databases. It isn't. It's very computational. There's no transaction semantics that are really helpful there. Now, of course, RAG is good. Language queries on retrieved data, data analysis, and even generating SQL queries, I think, is going to be really powerful. Again, some URLs here at the bottom if you're curious. So Postgres has a whole bunch of AI solutions. PG Vector I've already talked about. EDB has one, Timescale has one, Tembo has one. A lot of the cloud providers all have them as well. Okay. So in conclusion, I mentioned I was going to talk about how Google got us here. Again, the computer history of AI goes back pretty far. 2023, Word2Vec out of Google, foundational for what we're doing in terms of adjusting words that are next to each other. 2017, attention blocks, also by Google, okay? But ChatGPT really in 2022 is what allowed everything to take off. I think Google missed the boat because they were so focused on their core business, they did not really understand that aggregating different pieces of information together on the web in one format was valuable. Now you see that happening now when you do a search, it gives you an AI answer. Okay. But again, that was an afterthought only after OpenAI pretty much took that market. So again, disappointing. They're trying to do catch up. We'll see what happens. I'm going to leave you with two quotes. First quote, this is again URL here at the bottom of a video. A year ago, if somebody had said to me in my lifetime we'd have these capabilities of ChatGPT 4, I wouldn't have believed it, and now we have them. Okay, so with 1 year, what he thought he wouldn't see in his lifetime, he's now seeing. But keep that together with another concept, and this is a more philosophical one. He says, we are used to the idea that people or entities that can express themselves or manipulate language are smart. But that is not true. You can manipulate language and not be smart, and that's basically what large language models are demonstrating. Okay? And we have some URLs here at the bottom. The original is the quote. The other two are articles that are starting to come out. In fact, the bottom one, The Atlantic, just came out like 2 weeks ago, trying to explain that we're putting expectations on AI when we think it understands what it's saying, when in fact, it's really just doing statistical analysis for word prediction based on the words that we gave it, whether it trained those words or whether the words were in our query. So thank you very much. I am out of time, so I'm not going to be able to take any questions, but I will be here for the rest of the weekend. So you will not have trouble finding me to ask me whatever you'd like to ask me. And thanks so much.